Hi, in the previous video, we have performed operation on numeric type objects. In this video, we are continuing the same. So we have ended the previous video on the division, basically the true division and the floor division. So let's start this video from the integer precision. So division may differ slightly across the Python releases, but it's still fairly standard. Here's something a bit more exotic. As mentioned earlier, Python integers support unlimited size. What it's mean in this example, if we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So if we add this 30-digit number plus 1, it will give exact 31 digits. So this unlimited precision integers are a convenient built-in tool. They are also why we are able to raise 2 to the such large power. So we can raise 2 to the power 500 and we will get the exact result what it should be. Because Python must do extra work to support their extended precision, integer math is usually substantially slower than normal when grow large. However, if you need the precision, the fact that it's built in for you to use likely, there is some penalty of the performance. Complex numbers. So although less commonly used than the types we have exploring so far, complex numbers are distinct core object in the Python. They are typically used in engineering and science applications. If you know what they are, you know why they are useful. So complex numbers are represented as two floating point numbers, the real and the imaginary parts. So you code them by adding a j. So here example of complex number. Either you can give the small j or you can give a big J. Both represent the complex number. So we can also write complex number with non-zero real part by adding the two parts. So let's see some example on the interactive shell. So for example, if we have 1j plus 1j, it will give 2j. So it's a real number with no real part. Similarly, we can perform other operations. For example, we have a complex number 3 plus 1j and we multiply it with the 4. It will give you a 3 plus 4j. Also, we can do the same by enclosing the complex number in a parenthesis. So 4 will be multiplied both with the real and the imaginary part. Complex number also allows us to extract their parts as attribute, support all the usual mathematical expressions, and may be processed with tools in the standard CMath module. The complex number of the standard, and because the complex number are rare in most programming domains, though we'll skip the rest of the story here, and I will add the link of the Python's language reference manual in the description in case you are interested. You can go and check out there. The next part is hexadecimal numbers, octal, and binary literals. So Python integers can be coded in the hexadecimal, octal, and binary notation. In addition to the normal base 10 decimal coding we are using so far. So the first three of these maybe first seem foreign to the 10-fingered being, but some programmers find them convenient alternatives for specifying values, especially when their mapping of bytes or bits is important. So keep in mind that these literals are simply an alternative syntax for specifying the value of an integer object. So here are the octal literal. So we can define octal as 0 followed by O and the value. So this is octal 1, and its value, this value we can be ranged from 0 to 7. So similarly we can define 0, 20, 377. For hexadecimal, it starts with 0 and X and any number. So this value can be ranges from 0 to 9 and A to F. A to F nothing but 10 to 15 in decimal. So you can also give FF. Binary literals, so in binary we can give 0 and B and 0 1. This can be 0 or 1. So this is called 0 B. So Python prints integer value in decimals base 10 by default, but provide built-in functions that allow you to convert integers to the other bases, digit strings in Python literal form. Useful when program or users expect to see value in the given base. So for example, if you want to see what is the value of 64 in octal, we can simply use oct and give the 64. It will give 100. Same for hexadecimal and same for binary. So the oct function convert decimal to octal, hex to hexadecimal, and bin to binary. So there is also one built-in function called int that converts a string of digit to an integer, and optional second argument let you specify the numeric base, useful for numbers, read from files as string instead of code in script. So here is 64. Yeah, so here if we give the value in decimal, the interpreter returns the value in the decimal. If we give the same value in the octal, it also returns the value in the decimal. And also you can convert the same using the int function. So if you want to give int to 64, it will return 64. if you want to give int of 100 and base 8, it will return 64. Same, we can convert the hexadecimal of 40 and base of 16. It will return decimal value of 64, and same for binary. So also it supports literal for. For example, to get better readability of your code, you can give the number in the literal form. To avoid confusion for the decimal numbers, in the above example for base 8, 16 and 2, someone can consider the number written in the decimal form. So even though if you're writing this int and so someone may consider this as a someone may consider this value as an integer rather than a binary. So it may confuse that if you are giving the 1000 of 1000 or a 1 million. So better to write this. We can also write the same as int of 0x 40. So it will specify that you are writing a hexadecimal code and try to convert this into a decimal, or you can also give like this as this will show that this number is in hexadecimal form and this number is in the binary form, and we wanted to convert this into the integer. So this will return the decimal value. So this will avoid a confusion to the reader with these hexadecimal values to a decimal value. If you write in this form, people may confuse with this is a decimal value. So Python also provides both built-in functions and standard library modules for numeric processing. So there are some other built-in numeric tools provided by the Python to process numeric type objects. For example, the POW and ABS are the built-in functions, and this will compute the power and the absolute value. So here are some examples. To compute power, we can give two values. One is, so if you want to use if you want to compute the power of a value, so for example I want to compute the 10 to the power 2, so we have to give power bracket 10 and the number of power, that is 2 here. It will return the 100. Absolute is like, if I wanted to check what is the absolute value of 11, it will return this. So also here are some examples of the built-in math module. So math module is built in, but we need to import this first as import math. Then there are two standard way. So if you wanted to see what is the value of pi, it will return this. What is the value of exponential? So this is return the exponential value. If you wanted to calculate the sine, tan, theta, so math dot sine, and let's calculate math dot pi divided by 80. So this will return the value. So this is also available for the cosine and tangents. For summation, we have a sum function that will create the sum that will calculate the summation of all this sequence of numbers. We can also have min function to get the minimum of the given sequence, and also the max function. So min and max accept either a sequence or the individual argument. Notice that the standard library modules such as the math must be imported. But built-in functions such as ABS and round are always available without import. So, in other words, modules are external components, but built-in functions live in an implied namespace that Python automatically searches to find the name used in your program. This namespace simply corresponds to the standard library module called built-ins. So these functions lies in the standard libraries called built-ins. If we see in Python 3x, and in some reason if you're using Python 2.0, so those libraries are built-in. So that's all for this video. So thanks for watching and stay tuned.